Today, we still talk about the design of perfect reconstruction filter bank. Our final goal is to talk about wavelet filter banks, but we will come to that topic a little bit later. So we are still on the way, and actually we are talking about a filter bank which consists of 4 filters. We have 2 bands, 2 branches, and we can also imagine that the upper branch contains the low-pass filters and the lower branch contains the high-pass filter. H denotes the analysis part of the filter bank. F denotes the synthesis part of the filter bank. So to achieve the perfect reconstruction property, we have 2 equations to obey. The first one is actually non-distortion condition. Such an equation even stands if we have no decimation and extrapolation. In that case, on the right-hand side, there would be no 2 but 1. It is pretty obvious condition. If we have ideal filters like H0 and F0 are ideal half-band low-pass filters, and H1 and F1 are ideal high-pass half-band filters. In that case, we have no aliasing. Aliasing is cancelled by the filters itself, and we do not need the equation number 2. But the great idea is, even if we have real filters very far from the ideal, we can still, so we have aliasing, we can still design filters in such a way that the aliasing component cancel each other. So that was the brilliant idea, and that idea is expressed in the expression number 2, equation number 2. That aliasing cancellation condition makes some cross connections between the filters. Filter H0 is related to the filter F1, and filter F0 is related to the filter H1. Actually, they must have the same coefficients, but one of them must have alternating signs in such a way the aliasing terms will be actually cancelled. They will cancel each other. Okay, what will be our way how to design a filter bank? Actually, we will start with the low pass branch, with the upper branch of the filter. We will learn how to design the filters in a way to actually to obey the equation number 1. And then once we have them, then we will just use that very simple cross relation between the filters to write down the filters F1 and H1 of the high pass branch. So let's start with that story. Before going to the next slide, notice that in equation 1 we have products of the 2 filters, and again product of the 2 filters, product of the filters in the upper and in the lower branch. So we are introducing something that is called product filters. Actually, it's only we just denote the product filters. So P0 equals F0 times H0, and P1 is something very similar. So if we now write down the non-distortion condition, it is pretty short and compact, so it looks like this. So let's start designing. So here we have the recipe. Let P0 be a low-pass filter and P1 will be a high-pass filter, high-pass product filter. Okay. So the step number one will be, let us design the low-pass filter page P0 with some desired properties, but the one that meets the condition number one. Let's go back. So the condition number one, or okay, we have condition number one right here on this slide. So the P0 minus P0 of minus Z must be equal to 2 with eventual delay. Once we have it, so it is a product filter, so this guy, we will factorize it in two parts. So in any possible way, we can factorize the filter. Then we will have two filters, F0 and H0, whose product equals to P0. Once we have two filters, then it's trivial to get F1 and H1 using aliasing cancellation conditions. I mean, they would have the same coefficients of the impulse response, only with alternating signs. So let's start with an example. Our example will be based on, I mean, it is very, very often choice that the filters are of finite impulse response. I mean, even that example from the slide number 3 was also the filters with the finite impulse response. H0 had only 3 samples of the impulse response. F0 had 5 samples of the impulse response. It was definitely a finite number. Of course, the overall length, if H0 is FIR filter and F0 is also an FIR filter, the overall length of the response will be proportional to the sum of the lengths. Sum of the lengths of individual filters minus 1 if we want to be very precise. Okay, there are many ways how to design such a filter, and today you are going to learn the general principle, and you will be able to design a filter on your own. You can even name it by your name. We start from something that is pretty simple. So let our P0 filter be a low-pass filter. I mean, on this slide, you cannot see that it is a low-pass filter, but let it be. So we have, let it be an FIR filter of the length 6. So we have 6 numbers. Here we have a P0 of 0, P0 of 1, 2, 3, 4, and 5. I mean, the coefficients, the 6 coefficients corresponds to different delays. So this is the delay 0, delay 1, delay 2, delay 3, delay 4, and delay 5. So such a, if FIR filter of the length 6 has delay of 5. And any numbers work. If you want that such a filter be a low-pass filter, then you have to take care about its frequency response, but don't care for the moment. Okay, in our equation from the previous slides, you can see that P0 minus P0 minus Z must be equal to 2 times some delay. Okay, so we have to learn about this term. Let's go back to our example. So P0 of minus Z equals, so what happens? Let's take a look on this polynomial. The polynomial has odd and even exponents. Even exponents do not react on negative sign of Z, so they remain the same. On contrary, odd components change its sign. So wherever you see odd exponential, the result, I mean, that terms must change the sign. In our equation, we have the difference between the two. So we have a difference between the two terms, and it must be equal to number 2, eventually with some delay. What does it mean? Even shifts, even delays cancel out. If they cancel out, you can put any numbers you want. So you are completely free to put any numbers in that places where actually the delay is even. What happens to odd parts? Odd parts add up. So they add up and you have 2. So the result is 2 times bigger than the original one. And such a thing must be equal to 2 times, and you have some delay. Now we can learn that delay of such a filter cannot be any. Actually, it can be 1, 3, or 5. If you choose 1, in that case, this guy must be equal to 1, and all the others must be equal to 0. If you choose 3, which is in the middle, and it is the most common choice, here you can see a reasonable choice. I mean, all of them are reasonable, but let's say the common choice is to choose the middle one. So we have an overall delay of such a filter bank that is equal to 3. In that case, the middle guy, the middle term must be equal to 1, and the other 2 must be equal to 0. Okay, so this is the only thing you have to take care about. So we have 3 coefficients that we can set in any way we want, and we have 3 coefficients that must obey these 3 equations. And that's all we need to achieve the non-distortion condition. Okay. Sorry, I jumped somewhere, who knows where. Notice that even powers are missing from the expression, so the result is an odd function. Obviously, L must be odd, 1, 3, or 5. So to get a little bit more simple expression, we can multiply, both sides, left hand and right hand side, by z to the power of L. I will just go back. So if I multiply such an equation, left hand side and right hand side, with z to the power of L, the right hand side will remain only 2. So this is a no delay filter bank. So in such a case, we have filters that have no delay at all. Of course, they live only on paper, not in reality. But it is very nice, to do it this way. But by such a multiplication, that story about even an odd samples go other ways. Now you will easily notice that now odd terms are arbitrary and even parts disappear when cancel each other. So this is the way how it looks like. Now our perfect reconstruction condition looks like this. Notice that we have no 0 in index to make a difference. So let's say in normalized filter in such a way are denoted in literature like P. So P. Okay. Now all odd powers are 0 except one constant element, which is exactly 1, and that is in the middle. And the coefficients corresponding to even powers are our variables of design. Let's Okay, I will just go back for a second. There are many ways you can construct such a product filter. But for our final goal, it would be useful to start with something very simple. I mean, you will still have never forget that at the end you will have to factorize it in two parts. I mean, there are many ways. You probably know how to divide polynomials and to find the factors of some polynomial, but we are designing a filter. So why do not start with the factors? So maybe it is the better idea to start with some factors, so that we actually multiply to get the product filter. So let's do it this way. One possible and pretty good choice is that we have two terms. The first term is binomial. I can't select it, but this is the binomial that is actually on some even power. P can be 1, 2, 3, or even 77. So you're going to get a simple binomial on some high even power. And we are going to need the rest, polynomial denoted as Q, which serves to fulfill the previous condition, the condition from the previous slide. Actually, the first term has roots on the frequency pi, or maybe we can say the roots are -1. -1 is actually e to the j pi, so it's the same thing. And they are of some even multiplicity. The second term is some polynomial which has to be tailored to meet the non-distortion condition. We will see it very soon that if the polynomial order is 2 times p minus 2, in that case, that polynomial is unique. But we will not stop there, so you can use polynomials of bigger order. In that case, you will have some freedom of design. If we just choose the lowest order Q, in that case, such a filter is called max flat filter, and in next lectures you will see why that name. Binomial, of course, because it has that binomial part. So let's go with an example. Let P for the beginning be equal to 1. So 2 times 1 is 2. So we have that power of 2. Okay. How about the Q polynomial? So 2 times 2 equals 4, minus 2 equals, 2 times 1 equals 2, minus 2 equals 0. So our polynomial Q is of 0 order in that case. It's 0 order polynomial is a simple constant, so some constant. Which constant? Okay, let's check it out. So on the left-hand side, we have a difference. So only the middle term changes its sign. It has odd power, and if you put minus c, it changes its sign. We have a difference of the two. Most of the terms cancel out. Only the middle term survives. It adds up to 4. So we have 4 z to the minus 1. On the right-hand side, we have 2. Obviously, only one delay is possible. L must be 1. It is, of course, an odd number. When you put L equals 1, it is obvious that on the left-hand side, our unknown constant must be 1/2. And this is the product filter that fulfills our goal. So such a product filter will provide for non-distortion condition. We can, of course, observe the polynomial right here on the bottom of this slide, but we can go up and we can look at the first row of this slide, and we can think about how to factorize it into polynomials. Okay, it's easy. I mean, I have square there. So if I have square, maybe I can just put 1 plus z to minus 1 on the left-hand side, and I can put the same polynomial on the right-hand side. What happens to 1/2? I can put it anywhere I want. So I can split such a polynomial in 2 filters. There are many possibilities how to do that. For example, I can put 1/2 on the one side and the remaining part on the right-hand side. I mean, it's crazy because this is not a filter, it is only a wire, more or less. But it is also a system that will provide for non-distortion condition. Or let's say the second choice is a little bit better, more useful. As I have already said, you put one member of that binomial on the left-hand side and one on the right-hand side. You can choose whether to put 1/2 to the right or to the left. Maybe we can even take a square root, so we can split it in 2 parts and associate it with analysis and synthesis filter. Or one more degenerate case is the third row, where you put 1/2 on the reconstruction side. So the second choice is, of course, interesting for applications. Let's do it together. So, okay, we have the upper branch. How to create the lower branch of the filter bank? Which condition we have to obey? Maybe somebody knows.
The aliasing cancellation, right?
Exactly. So, I mean, you have that cross relation between the filters. So F0 will actually determine the H1. H0 will determine actually the F1, and the coefficients must be the same, 1, 1, 1/2, 1/2, with alternating signs. So the final result looks like this. I mean, here we have H1 and F1. They are actually the same coefficients with alternating signs. The blue line shows the frequency response of the low-pass filters, and the green line actually shows the frequency response of given high-pass filters. Altogether, such a filter bank has both perfect reconstruction with non-distortion and aliasing cancellation. So this is the first filter bank we have designed together. It was pretty simple. So our second example will be a little bit more complex. Let P be 2. So our exponent will be 2 times 2, 4. Let's check it out. So we have a binomial, the same binomial, to the power of 4. 2 times 2 minus 1 minus 2, sorry, equals 2, which means that the minimum size q is of order 2. So such a polynomial is of order 2. Now we will find out why 2p minus 2 is important. So, okay, this is the factorized version. Let's go on. So power number 4 leads to Pascal triangle of coefficients. So when you evaluate it, we got 1, 4, 6, 4, 1. Okay, this is the binomial part actually expanded. We have still unknown coefficients of the Q polynomial. So we have to multiply it together. I mean, this guy has 1, 2, 3, 4, 5 terms, and this guy has 3 terms. So altogether we have 15 terms after multiplication. So here you can see the 15 terms. They are actually split in 3 rows. And we can recognize that the middle row must be 1. It corresponds to the middle delay if that delay is actually 3. This guy can be any. This guy must be 0, any, and so on. So, you know, in that result, you recognize that there are 3 terms that are any, and 3 terms that must be exactly 0 or 1. So we are going to get 3 equations with 3 unknown variables. So we have 3 equations with 3 unknowns. For a second, we can go back. So you can easily put the polynomial q, which is of order 3 or 4 or 77. You can still achieve the non-distortion condition. Why not? But you will get a system that has that has a lot of freedom, design freedom. If you have exactly the polynomial of order, we said 2p minus 2, which is 2 in this case. In that case, we get exactly 3 equations with 3 unknowns, and such a system has only one solution. So we can solve it, any way of solving equations. We get that Q0 is minus 1 on 16, Q1 is 1 on 4, and Q2 is 1 on 16. So altogether, it looks like this. This is our product filter. How to factorize it? I mean, the binomial part is trivial. Everybody knows how to factorize it. Just take some parts on the left-hand side and some parts on the right-hand side. What happens with the remaining part, with the polynomial q? Of course, we can also, we can just leave it as it is. This is one way. If we just leave it, it must go either on the left-hand side or on the right-hand side. That's also a reasonable solution. But we can also try to find its roots. Since such a system has some special symmetry, you can see that this is the system which consists a lot of symmetries inside. We are going to get always the roots that actually has a modulus on which is reciprocal. Okay, so this is one of the consequences of such symmetries of such a system. There are a lot of symmetries in such a system because you have that binomial, you have that Pascal triangle, and of course if you choose delay which is in the middle, in that case everything is symmetric and you will get such a result. So one root is this, and the other root is actually the reciprocal of the same number. Okay, so how to choose the factors? The first choice is, of course, degenerate. So you can put one on one side, everything on the other side. I mean, it's not very useful, but it's still here. You can take only one term of the binomial of the left-hand side and all the remaining on the right-hand side. Maybe we can split it on half. So two terms on the left-hand side, two terms on the right-hand side. What happens with Q polynomial? It can go either one way or another altogether, or we can split it in factors, but in that case, such terms are not symmetrical. I mean, let's go back. I mean, due to that Pascal triangle, you will always have symmetrical parts that originates from the binomial, but they are not symmetrical if they originate from that Q polynomial. And the consequence is that you lose that symmetry. Symmetry is sometimes important, especially in image processing. It is a desired property. People from signal processing, they will say that such a filter has linear phase, which means that they are symmetric and they have constant delay. If you choose it in such a way that they are not symmetric, in that case you do not have linear phase, and sometimes let's say if you change something, it has no symmetrical influence on the result. We don't like it in images. So if you take care about that symmetry, it is easy to see that the filters can be both symmetric, so the odd length, or one can be symmetric, the other anti-symmetric, but then they are of even lengths, and you can just see it by looking at the numbers. I mean, not some great theory. If you have odd lengths, you only change every second sign and it remains symmetric. But if they have an even length, they become anti-symmetric, which also fills in category of linear phase filters. So here is, let's say, the resume of that story. So do you feel that you can design a filter, a PR filter on your own? I believe you can do that, so it's not a big deal. We learned, at first you construct any product filter, so you can start with any numbers. I will go back right here. You can put any numbers, and especially for the odd ones, you can put anything you want, and you will still have that PR property. When you come to the point that you have to factorize the polynomials, maybe it is better idea to start with some factors, and that is actually what we have done in the sequel. So we made the filters that contains binomial part. It will be pretty useful for construction of wavelet filter banks. And of course, we had some remaining part, and then also we can just keep it all together on one side, or we can also factorize it by finding its roots. So much about two-channel or two-band filter banks. Maybe we can just make a short introduction in what happens if you have a M-band filter bank with M filters in the bank, like for example in MPEG standard, the bank with 32 channels is used, and it is also maximally decimated. I will just make a sketch. So in 2 channels filter bank, modulation matrix looks like this. You have one column corresponds to basic component and one column corresponds to aliasing component. In multi-channel filter banks, you have no one, but you have M-1 aliasing components. Only one column is direct. It corresponds to our original filters, and the rest corresponds to aliasing. And you can still achieve that aliasing components cancel each other across this filter bank. We will not, it is not the topic of this course, but there are many nice solutions like cosine modulated filter banks and so on. And the trick is pretty much similar when we were talking about mathematical description of decimation by factor of m. We use that trick on the unit circle, so something like that is used right here to cancel all that other parts. So here you can see the PR conditions in that case, and this is the expression for the reconstructed signal. One can say, okay, such a matrix must be, must have some special properties, and you can actually see them from this slide 22. Okay, that concludes this topic. Are there any questions, or we can go on with the next lecture? Seems that you're okay. Are you? Okay then. I'm going to share another one. Okay, I will just change the camera. So, okay, so we learned how to design our filter bank. We started from the upper branch. P0 was actually the product of the two. Okay, P0 was the product of the two. But actually, we were designing P0, and then we were splitting it. We were factorizing it in 2 parts, and we have plenty of solutions. If our filters were actually looking like this times 1/2, it was our first and the most the simplest example. In that case, we could split it on 1 times And the question is what happens with 1/2, and in our previous example we put 1/2 on this side. But I just mentioned that we could even take a square root of this and put it on both sides. This is also a good solution, and now we have the same filters on both sides. Is it good for something? Let's check it out. So in some introductory lectures, we mentioned that linear transforms can be described by some by some matrix. In some cases, it corresponds to some matrix multiplication. So you have a matrix A that corresponds to some linear transform. Our signal can be expressed as a vector. And actually, matrix multiplication corresponds to a linear transform. But for example, Fourier transform can be expressed in this way, and you learned how to design such a matrix. If such a matrix was unitary, in that case, the transform preserves energy. Unitary matrices had some special properties. So actually, it was about its inverse. So it means that A conjugated and transposed times A must be equal to unity, eventually multiplied by some constant. So that was the condition for a unitary transform, for a transform that preserves the energy. Maybe we can just try to construct some of unitary matrices, let's say step by step. If I have 2 times 2 unitary matrix, I can just start putting the first element, which is cosine of some theta. Theta is any number you want. How to achieve that, let's say, unitarity? So right here, so the element in the second row, the first element of the second row must be sine, because cosine squared times sine squared will plus sine squared will be 1. And of course, in the second row, columns must be orthogonal, so you must put minus sine and cosine of theta. You can easily check it out that such a matrix is unitary, and it actually represents a rotation. So if you multiply some vector with such a matrix, the result will be a vector that actually is rotated by the angle theta. You can put any theta and everything is going to be fine. Obviously, rotation does not change the length of the vector, and it works fine. You can check that such a matrix will remain unitary if you multiply one of its rows or columns by, for example, -1. Nothing is going to happen. It will remain orthogonal. Maybe we can just notice that in complex plane, -1 is right here, but you can check it out that you can multiply such a matrix with any number, any complex number on the unit circle. So all complex numbers of the modulus 1, and it will still remain unitary. So that fact we are going to use for our Filterbank. But we do not have, this matrix consists of numbers. our modulation matrix actually had filters as its members. So our modulation matrix was something that has complex functions for its elements. So we define a new term. We can say that some matrix P of z is para-unitary if it's unitary for every z on the unit circle. So the elements of such a matrix are not numbers. The elements of such a matrix are functions of the complex variable z. That is our modulation matrix. We don't have to evaluate it anywhere, but on the unit circle, they must be unitary. In that case, we call such a matrix para-unitary, and such a matrix, if this is a modulation matrix of our system, it will correspond to a filter bank that is actually that preserves the energy. So the energy and the transform domain will be the same as the energy of the original signal. What does it mean, unit circle? Unit circle, okay, maybe I'll just add one more. How to describe it in a different way? It means, the modulus must be 1, since every complex number can be expressed in a polar way. It means that these r must be equal to 1. So such complex number has 1 in front, and then they can be discrete. So this is actually the equation of the unit circle for all omegas. And this is how it looks like. This is a definition of the para-unitarity for some matrix whose elements are functions of the complex variable z. And here you can see, okay, what does it mean, conjugate? If your matrix is a real function of the complex variable, in that case, the operator, conjugate operator, corresponds to change of sign. Finally, we can express it in this way. Such a filter bank, if that P is modulation matrix of some filter bank, it will preserve the energy. So on the unit circle, it corresponds to frequency response. The energy will be preserved. Okay. So let's write down our para-unitary matrix. I will just go back to. I will go back to the lecture number 6. Let us recall what was our modulation matrix. So I'm back. This is the lecture number 6, and we have our synthesis and analysis modulation matrix. I will just write it down on the paper so we can have it when I go back to our today's lecture. So our modulation matrix, I'll change that. I cannot do it without stop sharing. So I will just write it down and then change the camera. So I just write down our modulation matrix as it was. Stop sharing. Changing camera. And sharing the new lecture. So this is our modulation matrix. Okay. On the left-hand side, there was a synthesis. Oh, it would be more useful if I write down the synthesis matrix. But right now I can see that it must be, I mean, for para-unitarity, for preserving energy, this matrix must be like this. So again, I'm going back. Okay, stop share. I'm going back, share. So our synthesis matrix was F0. I'm reading the first column, F0 of minus Z. The second column, F1, and F1 of minus Z. Okay, I'm back. So look at the red one. And now we can see that F0 must be equal to H0 of Z to the power of minus 1. And then we can see that F1 must be equal to H1 of Z to the power of minus 1. I mean, the second row does not bring new information. It remains the same. So these are additional conditions, something additional that we have to achieve if we want that our modulation matrix will be para-unitary, which means that our filter bank preserves the energy. So this is an additional condition, orthogonality condition. So we already had two conditions, one to achieve non-distortion and the other one to achieve alias cancellation. Now we have three conditions where maybe I can just go back to our filter bank, sketch of our filter bank. So anti-aliasing conditions were some cross relations between the filters. But right now we have no cross connection. Now F0 is related to H0, so we have some additional relations between these two guys as well as these two guys. I mean, it is enough to calculate only the upper branch because the lower branch will be goes from the aliasing cancellation condition. What does it mean? If some filter is equal to another filter, but Z to the minus 1. I mean, replacing Z with Z to the minus 1 corresponds to reversing time. Like, I don't know, here we have Z plus Z to the minus 1. So if I just replace Z with Z to the power of minus 1, the result will be 1 plus Z. These two guys goes to the right. 1 plus Z, the same two guys go to the left. So it's like mirrored around the axis. So like samples are mirrored. I'm going to show it. Sketch. So if I have 1, 2, 3, now I have 1, 2, 3. So this is H of Z, and the red ones are H of Z to the minus 1. So such a thing is like a mirroring and the time domain. So orthogonality condition demands that we have the filters in the same branch have mirrored coefficients. We still have, of course, aliasing cancellation conditions. So something very similar goes on even for the lower branch in our filter bank. Altogether, our PR condition of an orthogonal filter bank with no delay looks like this. So the third condition resulted that we have only one way how, I mean, not only one way, but we must very carefully factorize our product filter. I mean, not all factorizations are allowed. If we just put e to the power of j omega here, we get the condition expressed, we can say, in the spectral domain. So this is how it looks like for an orthogonal filter bank, which means that power frequency response shifted by pi must add up to a constant. Such filters are called half-band filters, even if they are not ideal. I mean, I used that term half-band filter for ideal filters, where you have a low-pass filter across the half of the band. But right now, any filter of that form, this is a kind of released, relaxed condition, can be also called half-band filter. So if you just if you move it by if you move the frequency response by pi, altogether they must add up into a constant. So it looks, such a factorization looks like taking a square root from a polynomial. Like you have a square, you have a product filter, and you must find something that is to the power of 2 equal to p, which means you are actually finding a root of the polynomial. Spectral factors exist, I mean, they are real if p is greater than 0. There are many spectral factorization methods in the literature, but altogether we don't care. Why we don't care? Because we started with a very simple way of construction. I mean, we are designing our filters. So since we are designing them, we know the roots of the filters, and we know in advance how to split it up to get the spectral factorization, to get the root factors of our system. So this is the general form of our binomial. We also used Maxflat to describe such a filter. Nice. If let us multiply it with z to the power of p to get a no delay system. I mean, if you have no delay system, on the right hand side you have a simple constant. Okay, oh, our non-distortion equation. Okay, so we multiplied. Binomial part is easy to factorize. I mean, we have chosen even exponent. If you have even exponent, everybody knows how to split it in half. So we have the same thing to p and the same thing to p. I mean, notice that this guy is that was the reason why we are using no delay system to stick with our definition. So the half of this part is multiplied with z to the power of P, and we get two spectral factors of such a system. What happens to the right-hand side? On the right-hand side, we are going to use, our polynomial always contains reciprocal modulus roots because of the mentioned symmetries. Recall our examples. And orthogonal factorization demands splitting reciprocal roots in different factors, which means that the result cannot be symmetric filters except if P is exactly equal 1. So that was our 1/2. 1/2. You can, the square of 1/2 is 1 over square root of 2, and it is symmetric. Maybe I didn't mention till now, for all design methods we are talking about, there is one name related. It is actually a Belgian scientist, Ingrid Dobeschi. Many wavelet families are called upon her. So she made us actually that idea of using binomial parts multiplied by some polynomial q is hers, and she made several choices that have been named upon her. So let's see what we can do. Our simplest filter was exactly, put it right here. So P equals 1, and we split it in two parts. And each part was multiplied by 1 over square root of 2. Okay, we said that we have to multiply it by z to get this part. This means, if you still remember, the delay of such a filter bank was 1. If you multiply it by z, now delay is 0, and we have that spectral factors. Each spectral, factor has a root at -1. And in complex plane, its position is -1. So our product filter had two roots at -1 on the unit circle. Okay, right here. And actually, Dobeschi have chosen to take 1, 0 to the analysis side and 1, 0 to the synthesis side. On here, we can see the impulse responses of all four filters. So impulse responses are 1 over 1, 1 over square of 2, which is 0.7. So here it is, 0.7. And the next one is also 0.7. The same stands for both filters. Here is the impulse response. And the high pass branch has reversed signs of every second sample. So here it is. So P equals 1. If P equals 2, then we have 4. So our filter was 1 over 16 to the power of 4. And here we had something, I forgot the numbers. We can just go back to the previous slide, but okay, don't care. So we had 3 terms with some numbers, okay. This guy has 4 zeros right here at the -1. So when z equals -1, it disappears. -1 is also e to the minus j pi. So this is the position of -1 in the complex domain. And you have 4 of them here. Orthogonal factorization means that 2 zeros goes to the one side and 2 zeros go to the other side. Okay. What happens to Q part? If you still remember, there was some numbers like square root of something, who knows where, but one root was here and one root was here. They were on reciprocal positions according to the unit circle. So binomial part is clear. 2 must go left, 2 must go right. What happens with the Q part? Okay, 1 must go on one side, the other 0 must go on the other side. Which one goes where? So Ingrid have chosen that inside part, in terminology of signal processing, such a system is called minimum phase, goes to the reconstruction side. So we have a cross, and we have a circle for the analysis side. The corresponding impulse responses are shown right here. What happens with 3? Okay, again, we have 6 poles right here, 6 zeros right here, sorry. And 3 will go to one side, 3 will go to another side. But right now we have the Q polynomial has, it is of fourth order. It has 4 zeros. They are, since this is the real polynomial, it always appears in conjugate pairs. 2 guys are inside and 2 guys are outside, and they are on reciprocal positions. So the Dobeshy choice is to put internal ones to synthesis part, to F filters, and the outside parts, the outside roots to associate with the analysis part of the filter bank. And it goes on like this is how it looks like for 4 or even 5 roots. But the impulse responses are very far from symmetric. Okay, I'm going back. So this is pretty not symmetric. As well as this, as well as this. Even dB2 is very asymmetric. The only one which is actually symmetric is dB1, of course, because the square root of 1/2 is 1 over square of 2, and okay, it can be easily split in 2 symmetric filters. All the others are, let's say, pretty much asymmetric. So it was the first choice of the Ingrid Dobeshy, and her second choice was, okay, why we really have to, all that zeros from inside to go on one side of the filter bank. Maybe we can make a mix. So if you make a mix, for example, for 4, d equals 4, maybe 2 internal ones can go to the analysis filters and 1 can go to synthesis filter. In such a case, we have less, we can have a least asymmetric result. We we have a better symmetry than we had before. Or for 5, you can make even more. I mean, you will never get completely symmetric filters, symmetric impulse responses, but it will be less asymmetric if you choose it this way. So, so much about symmetries. It will bring us to 2 families of wavelet filter banks. Let me change the camera. I mean, if you put all the roots on from inside of the unit circle on the synthesis side, such a choice is named Dobeschi wavelets, Dobeschi wavelet filters. We will come to that a little bit later. But you know that even symmetric filters that are actually called simlets are also from the same author, so from Ingrid Dobeschi. And in many cases, they are much better for applications because they are not so asymmetric. They do not have an ideal linear phase, but they are much better than. So when you make some kind of mix, some roots goes to the left and some roots go to the right, but you take care that it is at least approximately symmetric. So simlets are also Dobeschi wavelets, but different spectral factorization. You notice that taking a square root of a number also has many solutions. For example, square root of 2 can be, I mean, negative numbers also fit. Negative numbers to the power of 2 give the same result. So you have 2 results for the numbers. In polynomials, you have several results. You have several factorizations, so you can choose how to do that. And actually, we were talking about different factorization of that polynomial by moving the roots on one or another side of the filter bank. I hope you were able to follow me. If not, we can discuss it some other time. It's like playing with roots. So you just write down the roots of the polynomial and then you put them on one or another side. Actually, even the combinations, if you do not put conjugate pair on one side, but you take one and take on one side and the another on the other side, then you are going to get the filters with complex coefficients. It can work on the digital computer as well. And then you can get total symmetry in such a case, even for p greater than 1. But it is not so often used because people like to have real coefficients. For many applications, it works fine. And simlets are pretty good filters. Okay, I can see that Julien has left. Okay, I'm back to the lecture and soon we will be over. So there are so many other solutions. For example, I said that we don't have to have a minimal Q polynomial. We can have much more coefficient, then you have some additional degrees of freedom in your design to achieve some desired properties of the filters. Maybe some authors like Saramarki from Finland, he actually he skipped the perfect reconstruction. He said, okay, almost perfect reconstruction is also okay because many applications are in compression, so you are going to lose some information one way or another. So almost perfect reconstruction filter banks can have some good properties of symmetry, even with real coefficients. And there are so many different designs by different authors like Wetterly, Unzer, and so on. We will come back to, we learned how to design filter banks. We learned how to design orthogonal filter banks, which are actually a special case. Factorization with care. And you can try on your own to design some filter bank of desired properties. You can even invent your own filter bank, which is good for some special cause. So much for today. Do you have any questions? Was I too fast in this second part?
No, I think the speed was good.
Okay. If you have any questions, you can also use email and write them down. So have a good time, and I'm not sure that we will see each other next week because there is a recording of the next lecture. Maybe we can make a plan so that you can watch it on your own, and we can discuss it in January when we see each other again, maybe live. So until then, bye-bye.
Bye. Have a nice day.
Bye bye.
Have a nice day.